speaking this seminar. And so first thing I have to mention is something really sad. This talk is dedicated to a friend of mine who passed away 2 or 3 weeks ago, maybe 2 weeks ago. And some of you might know him. So this talk is dedicated with sadness and also, well, essentially sadness because of his passing. So this talk will be in memory of my friend who passed away on the 16th of January, 2 weeks ago. Well, let's go to the mathematics of this talk. So let P be a prime number. Let P be a prime number, and FP is going to be the finite field with P elements. So Z over PZ. So this is a finite field. And it has P elements. This is not really important for the talk, but what is important is that it has characteristic P with P elements and of characteristic P. And what does that mean? It means that if I multiply any element by P, I'm going to get a 0. And well, that's essentially because if you multiply an integer by P, then you get it falling here, and then it just vanishes, no 0. So it has characteristic P, but also something else, and it's perfect. And what's the definition of perfect? So this means that for every X that I take in here, I can find another element in here such that this X is the P power of this one. So essentially what I'm saying is that in this field, I can extract P roots, okay? Take P roots. Okay, of course, not every field of characteristic P for a prime number is perfect. For instance, if I take this field and then I join a variable, this field is no longer finite. It still has characteristic P, but it's not perfect anymore. And this talk will be essentially about algebraic groups over such types of fields, imperfect. So we call them imperfect because they are not perfect, imperfect fields. So this one. There are more complicated ones like finite extensions of this one. Also, some finite extensions will be imperfect also. Okay, so I have now a theorem which I call, everybody, well, some people know it, and some people call it in a jocular way, in a funny way. They call it the freshman. The freshman screen. So freshman means first year student at the university, like a rookie, a beginner. The freshman screen. And what is this theorem about? What does it say? You'll see why it's a dream of the first year student. Yeah. Like an engineering student or a biology student or a medicine student. In the case, any field of characteristic P, like this finite perfect field or this infinite imperfect one. What they have in common is that they both are of characteristic P. So if case any field of characteristic P, and I take two elements in here, then this is true. This is a dream of the first-year student because, you know, if mathematics, if this were true always, then mathematics would be so simple, you know, and just take the p power of a sum and just distribute the sum and, oh, so the first-year students love this theorem. You know, it makes life so simple. But of course, it only works in characteristic P. And the proof, some of you might know the proof. Of course, you have to use the binomial theorem to you know, compute this. And when you do that, then you get the binomial coefficient. Okay. There will be, the I here varies between 0 and P. But if the I varies between 1 and P minus 1, so I'm talking about the middle term, excepting these two, I mean the ones that should be in the middle. If you do that, if you compute this binomial coefficient for these indices, then it's going to get something, you're going to get something like this. Of course, you get the P factorial on top. And then here you get I factorial and P minus I factorial. Okay, this I factorial is not divisible by P because the I is too small. It cannot be divisible by P because it, you know, it just reaches up to P minus 1. So this one is prime to P, and this one is prime to P for the same reason because, you know, the I is at least 1. So this is, you know, P minus 1 or can be P minus 2, etc. But again, you don't have any P's in here. And so this is co-prime with P, and but you know that this is an integer, and so there's a basic arithmetic theorem in arithmetic, elementary arithmetic. It says that if this integer divides the product and this one is co-prime with this, then it has to divide this. Oh, so I see what's happened. So this one is P times an integer. Okay, and so this is 0 because we are in characteristic P. Excuse me, I need to get that cap. And so that's why it works. You know, it's because of the characteristics. It's so nice, this theorem. Of course, it's false in general, but this theorem is crucial for what I have to do, for the groups I need to define. Okay, so now this is basic arithmetic, and now we move a little bit away from this to talk about some basic part of geometry. Okay, so I'm going to define in a quick way, of course, without many details. I'm going to talk about the affine line. Over K, actually over any K, arbitrary, over any field. Of course, we are interested in fields of characteristic P, and later we'll be interested in perfect ones. The affine line over any field K, in modern terms, not classical algebraic geometry. I'm talking, you know, Grothendieck style algebraic geometry. But to make things simpler, it's just a pair. And where here we have a topological space, and here we have the ring of polynomials in one variable. T is a variable throughout this talk. And this is a topological space. And I don't want to talk about what type of topology is. It's not important for what follows. Okay, but in modern algebraic geometry, we have to be careful. Of course, this is one particular scheme, very simple, but there are others that can also be defined as a pair. In some of those, we will see other schemes in which, so in case the viewer thinks that is mistaken, I mean, could be mistaken by the following, or led astray by the following fact that for some schemes, this space can be trivial. They have only one point. Okay, a trivial topological space with one point. But here, the ring that will come in here for more general schemes is more complicated. And so those schemes can be very complicated, even if this guy is very trivial, just one point. So we have to be careful about that. And that we will see those so-called infinitesimal group scheme. Okay, they have only one point here, but this is as an important, it's complicated. Anyway, here we're just talking about the affine line. Okay, this is very simple. And I'm going to view it actually as a functor. A functor on which category? The category of algebra, for any K algebra. I call it K prime, but this may not be a field, it's just a K algebra. And for any K algebra, as a functor, this one is, what does it do? It's very simple. It's just, you know, it gives you the K algebra back. And furthermore, and also what happens when you take one of these polynomials in there. You can view a polynomial, an element here, as a function on this, okay? And so every f in here can be seen as a function. As a function on this affine line. Okay, and it's just very simple. It's I can view it as a function. It's just evaluating the polynomial. You know? So if you take an element here, which is an element in this algebra, which can be very complicated, but all you do is you just formally take the polynomial and set the variable equal to lambda. So it's very simple. Okay, so this is a scheme. It's very simple, and geometrically you can think of it as a line. It's the affine line, so it's something very straight, you know, very simple. Okay, but we're going to eventually take the generations of the group scheme associated with that one. So what is that group scheme that I'm talking about associated to that affine line? So it is this. Let me read what I wrote here. One can endow this scheme with a group structure. And in that case, it's denoted like that, the additive group over the field K. And again, I view it as a functor on the category of K algebras, rings like that, you know, algebras like that. And map it to the category of abelian group. And what does it do? It just associates to this, any K algebra here, the same K algebra with its abelian group structure, just the addition. So we do get an abelian group. So this is just the additive group. It's the simplest, one of the simplest algebraic groups that we can think of. It has dimension 1 because the underlying space without group structure is this line. And so this is very nice. The additive group dimension 1, very simple, okay? And in algebraic geometry, there is a basic construction in modern algebraic geometry. There is a basic construction. Grothendieck identified this as a fundamental thing. Well, it's very simple, this construction. It's called phase change. Phase change. And so, what does it mean? If K prime is just above, is any K algebra, then I can view this additive group scheme. There is a construction called base change.
Sorry, Christian. I think there is a question from Semi.
When you write for the affine line, it's a pair of a topological space and a polynomial ring in one variables. Is there any uh, it could be any topological space
Any what?
placed there, and could it be any topological space X that we're writing there, or are we thinking specifically of the K algebra with a topological structure equipped on it that makes the operations continuous, or
I didn't want to go into detail, but
okay, it's the spec of the
yeah. So the close points here are maximal ideals, irreducible polynomials, and so forth. Is that the question?
Okay, so it's not any topological space, but specifically the affine scheme defined by the function field or the function ring.
For ring field. So this one is just it's as a scheme, it's spec KT. Okay. So when I write spec KT here, I'm thinking this X is the underlying topological space of the spectrum of K of T. So here you have the points of the maximal ideals correspond to maximal ideals and so forth.
Right. And if K is algebraic closed, then that's essentially the same as the
if K is algebraically closed, then you can identify the maximal ideas with the points, and then you get the affine line over K bar, which is something very well known. Okay. So yeah, this is the modern algebraic geometry, because K is any field. It doesn't have to be algebraically closed. Actually, it won't be, because it will be perfect, and
But then using base change, we could actually consider what happens if we extend the base field to the algebraic closure, or see all those things as residing in the...
You can extend this. You can extend the field to the algebraic closure, which is a particular case of this construction, and you get the usual affine line that people who worked on complex algebraic geometry know very well. And, it's very simple for them, maybe not interesting, over an algebraically closed field. But over other fields, this can be non-trivial interesting, because we'll see soon that there are schemes that look like this guy over an extension of K, but are very complicated at the base. That's the subject of this talk, really.
Okay, thank you.
Okay, so that's where I'm heading. Okay, so I can take K prime is any K algebra, but actually I will be interested in purely inseparable extension fields. Okay, but anyway, so this base change construction in geometry, in modern geometry, is built on the tensor product of algebra. So that's why this notation is still used in this case, even though this is not a tensor product of algebra. It's just a notation. Most people write it like this, as a fiber product, okay? Okay, but this notation is, you see, it's a bit cumbersome. It makes me write too much, So one just does this. Okay, and so this guy, if it's the additive group at the bottom and you raise it, you still get the additive group. Oh, but here now the base is different. It's a different. So let me put it. Assume that this is K is a field. K prime is a field for simplicity. Naturally, this will be the important case. Yeah. Okay. So field. It can be done in general, but I don't want to get into that. So this is just. Let's put it this way. If K prime is any field extension, this is make things simpler and sufficient for this talk. K prime is any field extension of K. Okay, and so you get the same additive group over the new field, the larger field. This one could be a purely inseparable extension of this. This could be a field of characteristic P. Like, for instance, you could take this guy, which is imperfect, And then you could take the K prime as FP adjoint the P root. Okay. So this is a purely inseparable extension of this, of that one of degree P, because T is a variable. So this we'll be interested in this for imperfect field. Okay, so this is very simple group theory. And this base extension construction is important, very important in geometry, because there are curves that or surfaces or varieties that have no points defined over the real number. For instance, if we have an equation with lots of only squares equal to 0, like if you have something like this, then you won't get many points over the real except 0, 0, 0. But over the complex, if you base change to the complex number, then you get lots of solutions over the complex number because it's algebraically closed. So this base change construction is fundamental in geometry. It's a basic thing. Okay. Okay, and this one, this additive group, this one is an example, a very simple one. Is an example of a linear algebraic group, also called affine. And why is it called linear? Because actually I can embed it into a group of matrices. Actually, this one as a functor is going to be isomorphic to the group of 2 by 2 unipotent matrices. So some matrices of this form, where this guy is variable, okay? And so this will be part of the special linear group of 2 by 2 matrices. It has determinant 1, obviously, okay? So as a function, because, so why? Because if you evaluate at any K algebra, K prime, any K algebra, then on the left, if you evaluate here, you get K prime with the sum. And here you're going to get this group of matrices. And if you multiply these, two matrices of this form, if you multiply 2 of them, you're going to end up adding up the x's. So sum here the sum is transformed into the product of matrices. So that's why this is called a linear group. You can use them as matrices, groups of matrices. Okay, but let's go back to the freshman's dream, that theorem, that wonderful theorem that simplifies life, makes life very simple for the first year student. So that wonderful, binomial formula. So now we're going to, for the rest of this talk, okay, it's a field of characteristic P. From now on, there's the field of characteristic P. Then, by the freshman stream, by the freshman-Green theorem, there exists a natural morphism. That come up too well. There exists a natural morphism, which is just to raise things or elements to the p power. Okay, why is it morphism? Because of the formula. Freshman screens, if you take a sum in here, you raise the p power, it will be the same as raising each summon to the p power and adding them up here. So this is a natural morphism because of that theorem. Yep. And I'm interested in its kernel. and there's a notation for its kernel. Which is a natural morphism. This is called the Frobenius. Frobenius raised to the p power. And the kernel has a name in algebraic geometry. I don't know who came up with this name, but it's alpha because of additive, I guess, alpha pk. Here, I'm emphasizing that I'm working over k because then I will raise the field. Okay, this kernel A alpha pk, of course, is a group scheme, and I think I'm viewing group schemes as functors. I have to tell you what the functor is. So, well, if I take any k prime, k algebra as before, this is just the set, the group of elements in k prime with p power is 0. And this is for every k algebra k prime. Of course, if this k prime is a field, you're going to get something very boring in here, because if k prime is a field and you have an element with p power is 0, then the only solution is 0. You know, so like, you know, I like to think of this formula as saying that this group has no meat over field. It's just nothing. It's empty. Not empty, 0. If k prime is a field, even an algebraically closed field. Okay. So there's nothing in here, and this implies that the underlying topological space that I mentioned before is just one point. So this has a trivial underlying topological space, but note that this k prime could be any k algebra. It could be an algebra that has lots of nilpotent elements, lots of solutions. This could be infinite for some choices. In fact, I'm going to choose one example where it is in fact infinite. This is
Christian.
Yes?
I'm confused. Is this alpha p or mu p?
No, this is alpha p, the additive.
Or mu p. What is mu p then?
Oh, mu p. Oh, mu p. Oh, okay. So that's a very good question. Thank you for that question, because mu p is another example. This is one type. This is one type of infinitesimal group scheme. And there's another type, also well known, which my friend here has mentioned, mu p. Okay. This is the kernel of the same map raised to the p power, but not defined over the additive, but over the multiplicative. So here, you get all the x's whose p power is 1, not 0. Okay, so that's the mu p. Okay, this is also called the Frobenius, but it's Frobenius for this group.
But alpha p is not the kernel of multiplication by p?
What?
Alpha p is the kernel of multiplication by p?
But multiplication by p here would be 0 because the characteristic is p, so the kernel will be everything. So it would be the trivial map. No, this is raising, not multiplying by p, this is raising to the p power. And
okay.
It is a morphism because of the theorem, Freshman-Green theorem, you know?
Okay. Okay. Something wrong?
Yeah, I think Christian's connection maybe dropped.
Yes. He has muted himself.
Sorry, Christian, you're mute.
Okay, well, thanks.
Okay,
yeah. They're not lost.
Yes, fine. Yeah.
But it is important in to consider the kernel you said is important for algebras. If we were looking at algebras in general, in that case, the kernel may be non-trivial and it's important to consider its structure, right? That's just a reminder.
Yeah. So, well, I don't know if I answered the question.
Do you have a particular example? Do you have a particular example in mind for algebras with non-trivial kernel?
Yeah, that's the one I'm going to give.
Okay.
So you asked about this one, but this one I'm not interested in. This one, not yet. At the end, I will be. But here's an example for that one. Well, this is one of the reasons why this is called an infinitesimal group. See, here I'm considering the rank of all formal power fields. That's why I use two brackets. These are infinite polynomials. Don't worry about convergence. These are just formal. And then it's like when you have the Taylor polynomial in calculus, and you consider the Taylor series, and then you consider the Taylor polynomial, which is just a truncation. So here we're truncating. We truncate all the infinite power series and disregard all the power series that have this power of t to the p to the r. After that, everything is zero. Okay. So what is an element in here? Just something like this. Sorry, that's a 1. A 0, a 1, etc. A whatever. And then after that, you get t to the p to the r, which is 0. So there's nothing. So let's not call it t, but the class of t here in this quotient. So you have just certain types of truncated powers, infinite power series, you truncate it to this degree. And here you have an element, the class of t, if you raise it to the p to the r power, you get 0, the class of 0. And this is not 0. So you have lots of elements. You see, this group is important to not to lose infinitesimal information. That's why it's called an infinitesimal group scheme. So here if you do this for that one, and you take all the x's in here, if you do this, then you're going to get all the elements in K prime that are a multiple of this guy. Yes, because this is the -1 is at the exponent, here r -1. If you raise this guy to the p, you get p to the r, which is 0. So here you have lots of infinite in many, because this guy is infinite, If your field is infinite, you have infinitely many choices for the a's, the coefficients. So you have something infinite. Lots of nilpoltines. So this is a non-trivial algebraic group. Okay. So remark. This algebraic group, the additive group, is just geometrically, it's just a line. So it is smooth. Smooth. And the French call it lisse. Very smooth, no singularity. Smooth or non-singular. It's just a line, geometrically speaking. ignoring the algebraic, the group structure is just the A1. It's very smooth. But this guy, which is contained here, is smoothness, or totally singular. Actually, totally singular seems better. It's easier to pronounce than smoothness. But this conveys that it contains no smooth subgroups whatsoever, nothing, totally singular. But of dimension 0. Yeah, dimension 0, because the topological space is just 1 point, dimension 0. Okay, and these exist over any field of vectors P, perfect or imperfect. Okay? But what I'm going to tell you is that over an imperfect field, there exist algebraic groups that are totally singular, smoothless in this sense, like this guy, but which are of dimension, of positive dimension. Actually, I will give you examples of arbitrarily high dimension. And those groups are really complicated for reasons I will try to explain later. Okay. Okay. So now we go.
Sorry for interrupting. For some reason, the screen, the camera adjustment is changing, and the clarity of the screen is fading away and coming back. Just to let you know.
Let me explain to you why that is. I had a telephone ready to record this talk, but that one broke and it wasn't working. So I had to use another one. And this one is a backup, which I, unfortunately, I forgot to disengage the feature that follows my movement, okay? So if I move too quickly, the camera will try to adjust and it will get, the vision will get blurry, but it will come back. Okay. It's out of focus, okay?
Okay.
So, and I don't wanna stick my finger into the phone because I might, make things worse. Okay. So let's hope we can finish the talk with this telephone and it will still be understandable. I'm sorry.
No, that's okay. Thank you.
Yeah, but don't become desperate because you'll get blurry, but it will come back and you will see what you didn't see before. You will see it eventually. Okay. Okay. So I'll try to, control my energy and erase slowly so that it doesn't get to, the camera doesn't get too blurry. Okay. Okay. So now we come to talk about Peter Russell. I use both names because Russell is a very common last name in the English-speaking world. It's like Gonzalez, like my last name, which is very common here. And actually in all Spanish-speaking countries. So Peter Russell studied forms of the additive group. So I'm going to explain what those are, okay, in a minute. Forms of GAK, where K is an imperfect field. Okay, and what are these monsters? Peter Russell studied forms. Let's give them a name. G, how original. Okay. Form G of GAK. And so what are these groups? We'll see that they do exist. These are algebraic groups over K, such that when I view them over the algebraic closure, I just get the additive group. Okay? And it is a fact that if K is perfect, then there are no non-trivial. I mean, if K is perfect, then this G is really boring. It's just the additive group at the bottom. So in this formula, this isomorphism, we've seen it before, okay? Actually, we saw it with K prime here. But anyway, this is K bar, the algebraic form. So if K is perfect, there's nothing interesting here. There's nothing to see, move on, move on. There's nothing to see, boring. Okay. But if K is imperfect, there are many. Many examples. One of the oldest, perhaps the oldest. Let's just, I don't want people to start writing to me, you know, telling me, hey, that's not the oldest, I have another one. One of the oldest. Example is due to Rosenbeck, a well-known expert on algebraic groups from the 50s and 60s, is due to Maxwell Rosenbeck around 1957. Let's see if I have it here. Yes, here is Rosenbeck's example. He constructed this example as a subgroup of two copies of the additive group, such that in the equation, the final equation is this one. And the A is in K, but it's not the P power, which is possible because we are assuming that the field is imperfect. So there is such a name, okay? And actually I should call it, well, that's a bad choice of letter. Because I have an A in there, yeah, okay? So that's better. And this looks like a variable that I like, okay? And so we could call this piece of T because it depends on the T that I've chosen. Anyway, they're all the same type. So this is the equation. And well, is it really a group? Well, yes, it is, because if you add two of these pairs, like X, Y, and X prime, Y prime, you add them up. Well, here, the sum is no problem because of the Freshman-Green theorem. Same here, and this is linear. So, you know, it actually is a group. It actually is a group. It's an algebraic group. And it has dimension 1. And it's a form. If you view it, so let's take this key out of the way because it's just bothering me. If I don't have to go all the way up to the algebraic closure. I just add to this K the P power. I mean a P root. Okay, so this is an imperfect field extension. So this guy, because this I can make over this bigger field, I can make this into a P power. It's going to be the P power of this one. Then I put it in. I have something to the P here, I make a change of variables, and it becomes just the additive group. Okay, so over this bigger field, slightly bigger, well, the P could be 100 million prime, a big prime number. Anyway, but this is a finite extension, purely inseparable of degree P, and over that extension,
I think, sorry, Christian, I think your connection maybe dropped.
We have to wait.
Yeah.
So I was wondering whether the number of such forms has anything to do with k modulo pth powers of k. I mean, right.
Should we email?
Yeah, I'm sending an email.
Okay.
Okay, yeah, he sent an email that he'll be back in a sec.
Okay.
Okay, yeah, he's back.
Okay, I'm sorry
Hi,
about
Kristen.
that.
Yeah,
No
yeah.
problem.
Okay, I'm back. Okay, let's hope I can finish this. I had a technical problem. Okay, so I was explaining that this is a form of the additive group. This is a group which is not the additive group, but if I view it over this purely inseparable extension, it becomes the trivial thing, the additive group. And so, but this one is smooth. I was also explaining that it is smooth. That if I take the derivative here, I get, a derivative 1. This one will have derivative 0 and also this one, but there will be no singular point. It's very smooth. And also because of the fact that this guy is smooth over here, so this group is smooth over here, so it descends, the smoothness descends, so it's smooth at the bottom. Okay, so, but since I'm a bad boy, I'm mischievous, I like to cause problems all the time, okay? So I will erase the linear part. Eventually, if I erase this linear part, I get a group that is totally singular, because if I take the derivative here, it gets 0 and also 0 here. So every point except the origin will be singular. So that will be a totally singular. But let me follow my notes to preserve some sense of order. Okay. So that was an example by Rosalie, okay? So this is bothering me. Okay, Russell showed that Rosalie's example is typical. Okay, so he gave a whole class of examples. So
does it is it parameterized by k modulo k to the power p?
Excuse me?
Are these examples parameterized by k modulo k to the power p?
Oh yeah. Oh, you mean if I change the t?
No, not t. K, the field k.
Oh yeah, the field k is fixed.
Yeah. So you have k modulo pth powers.
Yeah, I take pth roots. Yes, and I create purely inseparable extensions.
Okay, doesn't matter. We'll talk later. Okay, it's fine.
Yeah, I can actually do it for any power of p. So here. I take so Russell generalized the example by Rosenwald. And again, I have and now the polynomial is much more complicated. And all I need is to make sure that at least one of these is in K, but it's not a P power. Okay. If they are all P powers, then again I get the trivial thing. But if at least one of these, I mean, at least one, okay, one of these guys. One, from A1 to AM, if at least one of those is not a P power, then I get a real form, non-trivial form. And here N is arbitrary, M is arbitrary, and this one actually becomes additive over a more complicated extension. So this becomes the additive, but this extension now is take these roots, p to the n roots of each of the coefficients from A1 to AM. Then I get a non-trivial form of the additive group. So these are still one-dimensional, of course. Everything is dimension one so far. Smooth. The form of GA. Okay, so now I'm going to do what I threatened to do. I take the same equation, but I erase this guy. This is the guy, the linear part is what makes it non-singular, because if I take the derivative, everything that vanishes because of the characteristics, but this guy A0, of course, I have to assume this is not zero. If I take the derivative of this guy, I get something non-zero. But if I take away the linear part, I get a group like this, which is totally singular. It still has dimension one. And for any algebraic group, there is a definition of the largest smooth subgroup. This is the technical thing that I cannot talk about now, but it's in a book by Conrad, Gaber, and Prasad on pseudo reductive groups. You can find it there towards the end. Okay, so for any group, algebraic group, I can take the largest smooth subgroup, and for this guy, it's a zero. It is totally singular, smoothless. It contains nothing smooth. So the maximal smooth subgroup of this guy is trivial. So it's totally singular. And these are the ones that cause lots of trouble.
it's not a form of the additive group.
Excuse me?
Is it a form of the additive group?
Of the little group of the alpha?
Is it?
Not really, because the alpha has dimension 0, and this guy has that. So, you know, if you don't change the dimension by changing the field, the base change, you know, by making the base change. So this is, I'll tell you what it is. You know, it is related to the little alpha p, the bad guy, the infinitesimal. So that particular example, let me see, that particular example, I don't know if I wrote that down. No, I don't think I have the decomposition for this one. But any of that type will actually, for any algebraic group, you can always find a high enough power of the Frobenius morphism so that you can make this guy, this quotient, smooth. I write the Sm down because it's a smooth quotient. And this guy will have here an infinitesimal kernel. So this guy has dimension 1. There's a little group of dimension 0 inside, such that when you take the quotient, you make it smooth. And this is a general fact. And for that particular example, I can't tell you what this I is because I didn't prepare that example. But I have another one that will please you even more, hopefully. Example. I hope I'm not going over my time. This is one example. This is total singular K group of high dimension. This is what I'm going to show here. The total singular K group of high dimension. Okay. I take a T in a field of characteristic P, which is imperfect, okay? And I consider this extension, we've seen it before, degree P, purely inseparable, okay? But I'm constructing an example. Okay, and I can take this little devilish guy, this infinitesimal group, but over this field. So I'm working upstairs, okay? And there is a certain operation which is in a certain sense opposite the base change or base extension. And that is called the Bay restriction operation, okay? The Bay restriction function. I can start with the group upstairs and push it down to K. Okay, so this guy has dimension 0, but the fact that this extension is purely inseparable messes things up with the dimension-wise. This group actually, this is the example I have in mind. This group has dimension P minus 1, and P can be any prime, very large. So this has arbitrarily large dimension. Has dimension P minus 1, and this guy is smoothless. There is nothing smooth in it. Okay. Well, how do we need a lemma. We need a lemma to tell you when a group is smoothness, okay? G is totally singular for smoothness. If and only if it has no points over the separable closure other than 0. Okay, and so you can check that. You can try to find the separable point in here and use the properties of the Bay restriction. You see that this is 0, okay, because you get something here that has lots of things, but only infinitesimal. Okay. So this guy is still a singular. And using this general theorem, I can tell you what the kernel, this infinitesimal kernel is. And that, I think I will finish with that, okay? because at the time I don't want to.
Sorry, Christian. Before you wipe this page, I think Chandon has a question about this left board. Is
Yes.
H a form of GA?
Oh. Oh, this guy H?
Yep.
Yeah.
The form of GA, because if it were, it would be smooth. Remember that GA is smooth. And you know, by raising the field or lowering the field, smoothness is preserved.
Right.
And so
Sure.
this is not a form of anything that I know. It's not a form of GA because it's non-smooth. But you will see that it's very close to GA, actually to a power of GA. So, excuse me, can I erase now?
Yeah.
You'll feel better once you see this exact sequence. You'll feel better. I hope. So I'm not talking about, I'm talking about this guy. Oh, no, I'm talking about this guy. This guy is an example that I didn't work out completely, okay? This is just to show you that my purpose here was to show you that if you erase the linear part, you get an example of a smoothness. But for this age, for this guy, applying this construction, what's the largest smooth quotient? It is a power of GA, but it contains this infinitesimal. So here the infinitesimal kernel is alpha p. So here you have this exact sequence: alpha pk, Veil restriction of alpha pk prime, and then you get the quotient, this one. So this smoothness group, in a sense, is a deformation of this additive copy, a product of additive copy. GA p to the minus 1, you deform it, this is smooth, you deform it in a certain way, you get something completely singular. And in order to, tame this guy, you have to mod out by the infinitesimal alpha p. You take the quotient, you get something smooth. So these guys are badly behaved because, well, if you can consider the subcategory of all smoothness algebraic K groups, and try to see the property. Well, it's not stable by extension because, I'm sorry, it's not stable by quotient because you can have smoothness K group and you can make it smooth by modding out by something, by taking a quotient. So there you have a problem. There you have a problem. And so this subcategory is not stable by quotient. Okay, that's one of the many problems that you see. And to show you that there are many examples, this is just one particular example. I can show you this one. A consequence of that lemma that I wrote, a consequence of this lemma is the following. If H1 and H3 are smoothness, then, so here everything is commutative. I take an extension. So if these guys are totally singular and I take an extension, this guy is also totally singular. So once I get two examples, if I can make an extension, I get another. So you see, there are many examples, many. It's it's large, like Siberia. It's an undiscovered country. It's a new, well, for the masochists probably, because these are very hard, very difficult problems, difficult groups to work with, and they are always linear. One can prove that they are always linear, and if I take any algebraic commutative backwards. If I take any commutative algebraic K group there. As I said before, it contains the maximal smooth subgroup, and the quotient is smoothless. So the quotient of this by that is a smoothless K group. That is a guy like this, of this type. And that's my notation, the smoothless quotient. So in a sense, well, they are very important. Of course, here, if this guy is not linear, you know, here this guy will contain an abelian variety. Okay, but this is always linear, and this is smoothless, and therefore the category of these groups is very important. Over a perfect field, or a field characteristic is 0, then this guy disappears. Everything's smooth over a field characteristic is 0.
In this context, what's the term smooth mean? And it's smooth what? Smooth point, smooth group, smooth.
Smooth as an algebraic variety.
Yeah, smooth algebraic variety. Yeah, this is a smooth algebraic group. It has no singular points.
All points being smooth. All points being smooth points. All points of the variety being smooth points. You're using it in
the
that
map.
sense, right? No singularities.
You apply the Jacobian criterion in smooth, you know, the determinant, not 0 and all that, you know?
Okay.
So classical concept of smoothness.
Okay.
Yeah. It's different from regularity.
No, wait, they are related. A group is smoothless if it's geometrically regular, if it's regular over the algebraic closure. So regularity and smoothness are related. Actually, it's part of the definition of smooth. That is geometrically regular. Okay, but there are, well, I don't want to get into Cuscular curves because I don't have the time. Anyways, well, I wanted to show you these examples and that these groups exist and they are interesting to study and the category is big and they cause lots of trouble and one has to study them and you know this group actually appears quite often, or a few times, in the book that I mentioned before, Conrad Gaber Prasad on pseudo-reductive group. It's an important book. Okay. So this example in particular. Of course, you can also take mu p. Yeah, I was asked about this guy. This is an infinitesimal group of multiplicative type. So inside the torus, GM. So you change you change alpha by mu, and here you have something. This guy is also smoothless. And if you take out this guy,
one.
Excuse me?
Not 0, 1. It's multiplicative.
Yeah. Okay, I punished myself. Okay. One. Okay, that's a joke. Okay, I always do that with my students when I make a mistake. All right. So, all right. And so, what's the quotient? Let me see what the quotient was. I think the quotient was this guy. And this guy, the restriction of the multiplicative group divided by multiplicative group, this guy is a unipotent group, and I call it W because it's a unipotent. It's a K-wound, so-called K-wound unipotent K group. It's a unipotent K group that contains no copy of GA. It has no copy of GA inside. These groups were studied by Teets in the 1960s. Okay. So you get lots of interesting things here. Lots of very difficult to work with. But passionately interested, at least for me. Okay, but you know, I can see, I don't know about you, but I can see the beauty of mathematics mentioned by Russell, this time Bertrand Russell, not Peter. Bertrand Russell, you know, he says that mathematics is beautiful, you know, the famous phrase, and I see the beauty of mathematics here, even though it is technically very painful. But, you know, I'm drawn to it like these moths to the light at night, you know, and they get burned and they're like, okay, well, let's not be that pessimistic. But anyways, that's what I wanted to tell you about these groups. And I hope you found them interesting. And I'll try to publish something about these groups maybe next year, not this one. I guess it's a lot of work. Okay.
Thank you very much, Christian. Thank you for your very nice talk, and the audience can unmute.
It's not about the technical problems. I hope we can still get a recording, even if it's a truncated one, okay?
Yeah, sure. Yeah. So thank you very much. And the audience, if there are any questions, you may ask now.
Is there a classification of one-dimensional, totally singular groups?
Whoa, no, this is, you know, I think this is the first time the totally singular groups have been mentioned in the literature. It's not even published, you know. At least I haven't seen them. Maybe, but I'm sure the experts know about these, but there's nothing written about them. So there's no classification, not even for the one-dimensional, because, you know, I only showed you the work of Russell. One-dimensional groups are forms of GA. There may be others. There are others, you know. Like, I don't know if I start with one of these guys, maybe I can play with the equation, take something out, and produce a smoothly group. I don't know. I haven't. Let me see. I don't think I have the formula here. Can I do that? Yeah, actually I can do that. Okay, but not now because it's too complicated. But you know, you can, if you want to learn about these groups in a published setting, I mean a published paper, you can, these groups, they are not called smoothless or total singular, but they appear in one form or another in a paper by Totaro. Actually, he uses these groups to produce these objects, pseudo-abelian varieties, by Totaro. In that paper, this guy shows up. This guy shows up too in the construction of these pseudo-abelian varieties, which are extensions. What are these pseudo-abelian varieties? They are extensions of abelian varieties, but by groups, linear groups that are not smooth. And actually, I don't know if you can find an example in this paper, but there are examples of such groups where this one is smoothless, has nothing smooth in it. You see, in over a perfect field, there's a famous theorem by Chevalier, which says that over a perfect field, if you get a smooth and connected group, you can always express it in this way with an abelian variety and a smooth connected group here. And that totally fails over an imperfect field. So much so that there are examples, as I said, in which this G is an extension of an abelian variety by a smoothless, totally singular group, maybe even this one. Okay, so you see, the territory has increased dramatically because over a perfect field, everything is nice. By Chevalier's theorem, everything is nice. But if you work over an imperfect field, you get a new whole undiscovered country. Okay, where you know, where that question, I wish it had an answer. Classify all the one-dimensional smoothness groups. But I think that's going to be difficult to do. Painful. Okay. Very interesting.
Thank you.
All right.
We also have a question from Hadi, if you want to ask.
So thank you very much for your talk. It's very interesting. So if I have an elliptic curve over K and take the kernel of the Frobenius and then do the Weil restriction. Sorry, elliptic curve or K prime, do the Weil restriction to go to K of the kernel of the Frobenius. Do I still get the smoothness?
That's a good question. Let me see. Let me write that down if I can. So I think my friend there is taking an elliptic curve over K prime. I'm not assuming that this is an extension of an elliptic curve over K. Okay? I'm just taking an elliptic curve over the bigger piece. And I take the Weil restriction. And
of the kernel of the Frobenius.
Yes, I know. I'm going that way. I'm going. Just give me a minute. So I take the Frobenius. So raised to the P power. Okay. And I take the kernel of the, I assume that this E prime, so this is not going to be subjective, okay? So anyway, let's just call this. Oh yes, you said that Frobenius, okay, yes.
These are isogeny.
Additive. Let's just additive. Let's assume that this guy, this elliptic curve does contain this guy. There are examples of such elliptic curves, okay? Elliptic curves that do contain this additive infinitesimal group. There are examples. And so here I have an example because this is another elliptic curve, which is purely inseparably isogynous to this one, if you like the word. And actually I can just go to E prime without worrying about the subjectivity. So, okay, and so here you have this guy is smoothless. We know this guy is not an abelian variety. It's not an elliptic curve. Well, it is some object which has dimension p because it has dimension 1. Well, I don't know if it has dimension p. Maybe not because this is purely inseparable. You see, when they have purely inseparable stuff, the dimension gets messed up. I don't know what dimension this guy has, but this is an example of a. This is an example of a pseudo-reductive group. I think so. And this is, these were identified or mentioned by Renault many years ago. Actually, this is an SAG3 at someplace. That this guy is not an abelian, it's not an elliptic curve, it's not an abelian variety. It's a different animal. And this guy is smoothness, but I don't know about this guy has to be smooth because this guy is smooth. Okay, and this smoothness is preserved by Weil restriction, and so this is smooth group that contains this smoothless one. Okay, this guy contains nothing smooth, but this and this guy is smooth, and therefore the quotient is smooth, and that's all I can say. And but this guy is not an elliptic curve, and it's more complicated than that. Of course, you can. It does contain. Let me see. Which way does it go? Oh, yes. Example. Assume that this E prime is actually E extended by some E over K. And so in this case, this E is embedded in here. For this particular case, so this guy contains an elliptic curve, but the quotient is, I said pseudo-reductive, maybe I meant this guy, the quotient pseudo-reductive, this guy. This is the one I meant to say pseudo-reductive. or maybe this one, I don't recall. Anyway, sorry about that, I didn't prepare this. But so if this guy contains an elliptic curve, but it's not an abelian variety. It has something weird in here. That quotient, and it does contain something smoothless, but it's not smoothless itself. I don't know if I answered the question, but that's all I can say about that particular example that I think is where the person who posed the question was heading. Is that right?
I mean, actually, I was talking about the Frobenius, not raising to the pth power, the relative Frobenius of E prime. Yeah. And not the raising to the pth power, and then taking the restriction, the Weil restriction of the kernel. But it doesn't matter.
Yeah, this is the restriction of the kernel. Yeah.
No, but you are
one of the examples is smoothless. But see, you have to be careful with the Weil restriction along purely inseparable extensions, because this is not going to be an abelian variety anymore. If this were separable, then you would get an abelian variety. Okay, but when you get purely inseparable, you know, everything just changes. Okay? And you can view some examples of these weird things in the book that I mentioned a couple of times now, where the first 20 pages or 30 pages, you have lots of examples of where even this is probably discussed. I don't recall exactly. Okay. Sorry about the incompleteness of my answer, but that's all I can think about now. Okay.
Thank you.
If there are any more questions, you may ask. If not,
there's a question in the chat box. I'm not sure if it was already.
Oh no, it was from before.
Okay.
Okay, guys.
Okay.
It's been an honor, and now I think I didn't have to go biking in the morning. Sure. I already sweated again, so I have to take another shower.
Sure. Thank you very much, Christian. Thank you.
Thank you
for your excellent talk. And I'll be in touch for sending you the recording.
The recording, yes. Many thanks for that. Okay.
Sure. Thank you very much.
Stay safe. Okay.
Sure.
Put your mask on. Okay. Bye-bye.
Bye. Okay. Maybe with I just stop the recording.